we can get a lot out of our data. There's a lot of information that's held within image logs, and hopefully what you walk away from this talk are ideas in which you can take something that is often used as a qualitative interpretation tool, for visually looking at what's going on along our wellbore. Obviously, we do structural interpretation and things like that, but take some of that qualitative interpretation and make it a little bit more quantitative. And we're going to talk a little bit about that today. Now, I will warn you guys that I'm only sort of scratching the surface here, and for this kind of subject matter, I could use 2 hours, maybe even half a day or more to really do the justice to each of these topics. So if there's something that I touch on that you're particularly interested in, don't hesitate to reach out to us or to your account managers to set up a one-on-one meeting so we can get into things in more detail. So this is the roadmap that we're going to follow today. We're going to start off with talking about how you can apply borehole image data, how you can use it, which is part of the reason for the polling question. And then we're going to spend a little bit of time going over the general workflow for working with borehole image data, from processing through the interpretation side of things. And then we're going to spend the bulk of our time in the application within Geolog, looking at our tools for not only QCing data when you bring it into Geolog and doing speed corrections and processing the images, but more importantly, and where I hope to spend the bulk of our time, is on the image analysis side of things. We're going to talk a bit about dip interpretation and fracture analysis because they're definitely very important. But where I get really excited, I mean, I'm a structural geologist, don't get me wrong. I love dip interpretation and working with stereo nets and walkout plots and things like that. But where I get really, really excited is when, with borehole image data, is working with some of our statistical analysis tools like threshold analysis and things like that. So we're going to spend some time talking about some of these tools like dynamic threshold analysis, and we may get into porosity estimation. I may not have time, so we might have to come back to that another day. And then we're going to round things out and talk about textural interpretation using 2D self-organizing map and multi-resolution graph-based clustering. And then we'll wrap up and open the floor up for questions. Okay, so I think most of us have a general idea of some of the ways in which borehole image data can be used. Obviously, interpreting our dips along our borehole image to get an idea of what our dip regime or what our structural regime is, or even, when we're interpreting bedding and cross bedding to get an idea of perhaps paleocurrents, getting into more sedimentology in that sense. We also use image logs to pick out fractures, do fracture description, get an idea of what our in situ stress regime might be, and as Samita said, my background's in structural geology, and I'm more recently trained as a petrophysicist, and the fact that I can sort of marry both of those worlds and take information from the borehole image from the structural side and incorporate that into petrophysical interpretation is something that makes me very happy every single day. So from a petrophysical side of things, we can start looking at getting a better idea of net sands. And one of the things that we did up in the oil sands was use image logs quite often to help us identify what might be a baffle or barrier for building a steam chamber. We can also obviously do facies analysis and textural analysis as well, and pull all of that information in to start making inferences on what's going on along our wellbore in terms of heterogeneities, both from a porosity and a permeability standpoint. Okay, so the general workflow with image data, regardless, I think, of what tool you're working in, is more or less the same. You're going to get your raw image files that are generally going to be in a DLIS file that you're going to load into your application. Once the data is loaded in, you need to QC the data, do speed corrections, and process the image. That's a typical part of the image processing workflow. Okay, so we're going to go through this a little bit, but we're not going to spend a whole lot of time on it, just because for me, as important as that is, I want to focus on what we can do once the data is in, once we actually have an image log that we can work with. Now, obviously, one of the things that we can do is borehole shape analysis. This is going to help us, look at where we're engaged, where we start to see breakouts, where we might have washouts, things like that. It also gives us an idea of what our semi-major and minor axes are as well. And you'll notice with this particular workflow, I've got 4 key boxes here. So I've got image analysis, structural analysis, fracture analysis, and textual analysis. For me, image analysis, all of this is part of image analysis, but when I talk about image analysis on the left there, I'm really talking about more of a statistical approach to image analysis. So threshold analysis, looking at sorting in a sense, getting at high resolution porosity, even a high resolution sand count or bug index, as a for instance. The structural analysis, this is often the bread and butter of image log interpretation. It's where we do our dip interpretation, and we can take that information, those dips that we're interpreting either by manually or automatically, and display them on a stereo net or on walkout plots and start making inferences of what's going on structurally along our wellbore. Do we see a sharp change? That could indicate a fault. Do we see gradual changes? Well, that could indicate changes in direction for sedimentation, or it could also indicate maybe a fold as opposed to a fault, right? Fracture analysis is also one that's is quite often used these days. It helps us start to make decisions about how we might want to complete our well, or things of that sort. So looking at fracture density and fracture aperture or fracture width. And then, finally, we've got textural analysis. We can look at an image log and make some sort of general interpretation on the texture visually. What the textural analysis part of the workflow does though, is it takes that visual qualitative interpretation and allows us to become a bit more quantitative, okay? So we're going to spend the bulk of our time in the actual application. So I'm going to go ahead and jump into geolog right now, and we're going to go through each of those and sort of in a workflow format. And we're going to start off with where we always start off when it comes to data. We're going to have a DLIST file. In this instance, the DLIST file has already been loaded. Okay, so once you get that data into geolog, you've loaded your image log data. What comes with that image log data is often a bunch of inclinometry data. So you'll see here under the geology section, we've got borehole image processing and borehole image analysis. So we're going to start off in the processing portion here, and you'll see here we've got things broken out by wireline, LWD, dip meter. We're going to spend the bulk of our day working with wireline images because the data that I have happens to be FMI data. Okay, so we're going to take a look at, so when you first get into your data into geolog, one of the very first things you're going to want to do is QC the data. So you're going to want to QC the orientation data, make sure it all looks good. And if it doesn't, you need to run some corrections on those. That's what the inclinometry QC workflow is all about. And I'm not going to go into it here today, but it is something that if you want more information, we can certainly cover in a private session for sure. But what you'll notice in the wireline images that we then have things broken out by vendor, okay? And under each of the vendors, we have the different tools. And what you'll notice when you look at each of these tools is that we've got things laid out in pretty much the same way. It's set up in a workflow order. So our R&D group did a really good job of arranging these menus so that all you have to do is just go from one step to the next in the workflow here, and it just sort of guides you through the workflow process. So we're working with the FMI data here. So under FMI, you'll see we've got a QC layout, and that's what you see on the main part of my screen here. The QC layout is really quite nice. With each of these different layouts, we have an upper section, and these upper section have a series of points that you need we think you should be aware of and what you should look for when you're QCing your data. So consider it a guide or tips and tricks for QCing your image log data. What this layout also does, though, is it provides us all of our orientation logs for our image log data, our accelerometer, so we can see if we've got any significant stick pull events, which are going to impact our speed corrections. And then we've got a display of each of our pads and flats here, so we can review the data and see if we see where we've gotten perhaps have any kind of bad button data or anything like that. So this gives us an overview of the raw data before we actually create an image log. Once we've done that QC, the next step is to actually do the speed correction. So we would run speed correction on our data. And then once we've done the speed correction, actually generate an image and then equalize and normalize that image. And what you're going to end up with is something that's going to look fairly similar to this. That's what this processed image layout is going to provide you, is something that's going to look very much like this, where we've got our raw image. This was what's generated from image generation, and then when we run equalize and normalize, we get this equalized image, and then we get a static and dynamic normalized image. And on this particular layout here, you'll see on the dynamic image, I actually have some sinusoids. In this instance, I've got a partial sinusoid that's picked here, a couple of partial sinusoids. And you can see I've got some fractures. I've defined these different categories as fractures or as cross-bedding or things like that. So we can start doing some of our interpretation directly on these image tracks here. So I'm switching gears a little bit now. As I said, I don't want to spend a ton of time on the processing part of it. I do want to spend more time on the image analysis portion of the workflow. So we're going to jump into the dip analysis part here. And you can see I've got, if I zoom in a little bit, you can see I've got the start of an image dip picking interpretation done here with a series of conductive fractures. You'll see I've got some partial sinusoids here. And when we come under edit dips, we can manually come in and select what our dip category is and interpret our sinusoids directly on this image track here, which is really quite handy. I'm going to move to a different workspace though, because that's only the tip of the iceberg when it comes to the dip analysis workflow. So manually picking our dips gives us a lot of control over how we define our different dip categories. You'll see here that with this particular well, I'm displaying several different dip categories. In this particular frame, I'm looking at conductive fractures here, and you can see I've got a 3D image here of my borehole image logs with the planes of my fractures displayed on here. And you'll see here, if I want to, I'm just looking at existing dip categories here. I can display all. So this will show all of the different dip categories that we have defined in the project by default. And I have control over these dip categories. I can come in and edit the properties of them, or I can create new dip categories if I need to. So we give you a lot of control over the manual interpretation of your dips. But we also have tools that allow you to do automatic dip calculation, and that's our auto dip tool here. And what this auto dip tool will allow you to do is go in and estimate dips or pick dips automatically, but we're not using conventional dip button correlations as a lot of tools do. We're actually going to use the entire image, and we're going to use contrast and continuity and edge effects and pick dips that way. And in this manner, what we're doing is simulating the interactive dip picking workflow. Okay, so we can run this and we'll get a series of automatically picked dips based off of image contrast and edge detection and things of that sort. Aside from dip analysis, we also have fracture analysis, and you'll see on this image, I've got conductive fractures that I've picked, and we're going to talk about these last two tracks on the right now. So under fracture analysis, we have two modules. One is fracture density, and the other one is fracture aperture. And it sounds like a lot of people do utilize these tools, whether they're in geolog and other tools, quite often. I know it's something that's become more and more popular, especially within unconventional workflows, or really just understanding the stress regime along your wellbore. So we'll talk about fracture density first. And one of the really nice things about the tool that we have is that we allow you to specify dip categories. So you're going to use your dip category to quantify or to count to give you your fracture density or your fracture count. And you're not limited to one dip category. You can actually add multiple dip categories if you so choose. In this instance, we just ran for conductive fractures here, but if I were to run multiple dip categories, I could output a fracture count for each of the different logs, and that's what this parameter here allows us to do. Okay, and so if we look at this here, this second track from the right is our fracture density track. And what this module is doing is on a depth by depth basis, based off of the parameters that we've got, our window length and our step length, it's going to go on a depth by depth basis and count the number of fractures and provide us with a density of fractures over that depth window. Okay, and our module help here, as with all of our modules within our image processing and interpretation workflow, does a really good job of explaining what the module does and what the different parameters within the module are. So if you are working within geolog and you're not certain about what a module is going to do within the borehole image workflow, I definitely recommend taking time reading through the module help. Okay, we're going to talk about fracture aperture next. So we've got, in a similar manner that we do fracture density, we can calculate the width of our fractures based off of, it's going to be based off of dip category. And again, we can specify more than one dip category. In this instance, we're just using our conductive fractures here. And we've got two different methods for going about calculating our fracture width. We've got the Luthi-Swaite method, which is what was used to calculate the fracture width for this particular data set or for this particular well. And again, the module actually goes into really good detail of explaining how the Luthi method works. But we also have an uncalibrated method. And what this is going to do, instead of using RXO, it's going to use a mean image value around the fracture to help estimate the fracture width. Okay. And so you can see here, alongside my fracture density, I've actually got my fracture width. Okay. So what I just covered, and I know I went through both of these really quickly, but the dip interpretation, the dip analysis and fracture analysis, I consider these sort of the bread and butter tools of the image interpretation workflow. And they're very important, and while they're really important, I want to actually spend some time on some of the other statistical methods. So I'm gonna actually switch gears a little bit, and we're gonna talk a little bit about what I'm going to call roughly image upscaling, or really what I tend to talk about in terms of statistical analysis, really. And under this, so if we come here and expand borehole image analysis, you'll see, before I get to the image analysis section, we're going to talk about borehole shape analysis. And borehole shape analysis is actually a really easy module to use. We provide you tools for whether you've got resistivity image logs where you've got 2 calipers, or whether you're working with acoustic data where you might have a radius image log. But the workflow for both of these is the same. Okay, and this is what the module looks like. And you basically come in and specify a tolerance for what your bit size is, so what's in gauge or not. And then you specify thresholds for where you've got breakout versus washout. Okay, so we're going to use these parameters plus our caliper logs, our P1 azimuth log, and our bit size. And what we're going to get from this module is a borehole flag, an azimuth breakout log, as well as ellipticity and min and max caliper logs as well. And we've got a nice little layout that comes with this. So you just pop up the layout after you've run the module, and the log should be populated, and you'll be able to see the results kind of like this. You'll see I've on this layout, I've got 2 3D image tracks that are displayed. One's showing me my radius image log, and the other one's showing me my dynamic, my processed image log, in this instance, my dynamic image log. And I can rotate that and orient it however I need. And then we've got this borehole shape track here, which is going to show us our semi-major and semi-minor axes, along with where our caliper arms sit. We also get this ellipticity log here that you see, and you can see where I start to see some enlarging here. My ellipticity increases because obviously I've got some things that are happening here. I've got results for azimuth breakout here, and if I scroll up here, we get this borehole flag, and this is actually really nice because it gives you a very visual way to see when you're in gauge, where you start to experience breakout or hole enlargement, or where you've got this gray here, where you might actually have washout. Okay, so this flag can be a really good visual indicator of what's going on along your wellbore, and it's easy to sort of key your eye into. Okay. So now I'm going to switch gears a little bit. We've talked a little bit about borehole shape analysis, and we're going to get into image analysis. And this is where I start getting really excited. We're going to start off by talking about image flattening. I'm not going to spend a whole lot of time on this, but when you're doing any kind of image analysis, really you want to try and remove the structural dip, so that because if you have a lot of dip and you've got these big arcing sinusoids, it can actually impact your image analysis, and you don't want to bias it by the structural dip. So we provide a tool for you to basically flatten the image, and you should generally start off by doing that, and we're going to assume that has been done on this data. The next step in the workflow, or it's actually really not a step, but the next thing you can do is run something called image statistics. Now, this is a pretty neat little module, and what it allows you to do is it allows you to determine different statistics that you can output from your image log. So in this instance, I would use my equalized image, and here you'll see I've got all of these other options up here turn to yes. And these different options are, I want to calculate a mean, a median, a standard deviation, min max, a range, and a vertical standard deviation. And I want to use a window size of about, in this instance, the default is 3. So that means it's going to take it, it's going to step 3 frames to calculate each of these logs. You can increase that to a larger number to increase your process or to speed up your processing time if you want. I tend to let the defaults run at least initially and then go from there. Now, some of the results from this get used in other parts of the image analysis workflow. For instance, you might use the image mean as input for porosity calculation or for calibrating to porosity logs as a for instance. So there's a lot of use that you can get out of these. Not much I can show you, but it is a really nice little module to be aware of. And what we are going to talk about first before I go into histogram analysis and the different threshold analyses is a tool that's been around probably for quite some time, and that is a tool for doing image binarization. And this was really, I think, in my mind, one of the first steps into sort of a statistical analysis of our image logs, or at least in my mind it is, and I could be wrong about that. But that's sort of how I've always thought about it. And what you do here is you use a cutoff log for your image log, and what you output is a binarized image. Okay, and if you're working in sort of a clastic environment, what this is going to give you is a very high resolution sand count log, or sand volume log, if you will. If you're in a carbonate environment, it might give you a bucket index as a for instance. And when you run that, what you're going to get in this instance, with this particular well, it is actually a sand count that we output, but we get this binarized image log here too. And you can use this, and we use the shale volume as our flag here, but we can use the sand count log to calibrate to whatever our shale volume, to help us calibrate our calculated shale volume to it, or if we've got core data, we've got core XRD, we can use this information to help give us a more high resolution idea of what's going on in terms of sand and shale volumes in a very rough, gross sense. Okay, so this has been around for a while, but I got really excited a few years back when we started adding some new tools. And one of the tools that we added was this histogram analysis tool. And this guy is actually pretty neat. We basically specify how many bins we want it to find, and then we basically say, give it some percentiles for cutoffs, right? And you see we have 5 different cutoffs, and I'm using a P10 for my P1 through P5. I'm using 10%, 25%, 50%, 75%, and 90% in this instance. And just to give you an idea of what's being used here, I'll bring up this guy here, and we're going to pop him out. We're going to use them a couple of times here. So basically, if I were to plot up my 10 percentile, my 10, 25, and 50 percentile here, it's the values from this histogram that we're using as part of this workflow. And so if I come in here, you can see here, if I restore this, so we've got this guy here, the sorting calculation method. When we go into the module help, what you'll see is that sorting calculation method here. This is something that's used for grain size distribution analysis. Okay, and we've got 4 different equations to use for this sorted calculation method. And in this instance, we're using this first one here, where we're taking P5 minus P1 dividing by 3. So we're taking our 90 percentile, subtracting the 10 percentile from it, and dividing by the 50 percentile here. Okay, so we're using this to get us our histogram image log here. So I'm going to close this guy, and we'll minimize him. We're going to come back to him in a bit, the histogram in a bit. What you get though, when you run this particular module, we go to histogram analysis, we're going to get something that looks very much like this. So when we ran this module, we used the equalized image. You'll see here I've got an array histogram here displayed for my image log, but I'm also displaying that histogram that we calculated as an image log. Okay, and you can see there are some logs that are plotted on this. Those logs, the black is the P10, the purple is a P50, and the brown is the P90. And one of the reasons I get really excited about this is because I can look at my image here and you can see we can get into this area right around 29, 25. This is, you can see here, this is actually a conglomeratic section, I believe. And so it's a bit more, there's a bit more heterogeneity here than we see in other parts of the wellbore image. And we can see that our P10, there's a bit more distance between our P10, our P15, our P90 logs here. And you can see that in our image log, there's a bit more, there's a bit more spread on the noise there, right? And if we scroll down, when we get into this area here at about 2935, it's much more homogeneous, and those three logs are sitting much closer together. You'll see immediately to the right of that, we have our sorting index, and our sorting index in this sort of homogeneous zone is relatively low. When we get into this another conglomeratic section down here, and we see that sorting index is increasing quite a bit. If we go back up to this other conglomeratic section, we'll see that sorting index is a little bit higher there as well. So, visually, I can look at the log and say, this zone is a bit more has a bit more heterogeneity than this zone down here. That's a very qualitative interpretation. But what the histogram analysis allows me to do is make a bit more of a quantitative interpretation from that data, which is, let the numbers speak for themselves, really, which is something that I'm a big fan of as a scientist at heart. Okay, so that, for me, I got really excited when I first saw that, but there was another tool that I get even more excited about, and that is image threshold analysis. And I think for me right now, this is probably one of my favorite tools when working with borehole image data. What we can do with this particular tool is we can specify how many cutoffs we want to work with, okay? We're going to use 3 for this particular example, but you can have as many as 9 cutoffs. That means you can have as many as 10 different classes, okay? And I said we would use the histogram again. We are actually going to use it right now. We use this histogram to come up with our initial cutoffs. So you'll see my first cutoff is at about 160, which is a little bit less than my 5 percentile value here. We're using 430, which is ever so slightly less than my 50 percentile. And then we're using 720, which is pretty much spot on to my 95 percentile, right? So we're using these as my cutoffs. So my first class is going to be from 0 to 160. My second class is going to go up to about 430. My third class is going to come up to about 720, and everything to the right of 720 will be my fourth class. That is what this, the image thresholding module is doing, okay? We use the equalized image, and we're going to get 4 different class logs. We're also going to get a major class log, but we're also going to get an image log, a threshold image log. And it's these guys that gets me really excited. It's the output here. So if I pull this guy up, what we can see here, okay, we've got this histogram that we calculated in the previous step, right? We've got our equalized log that we used to run the module. And then to the immediate right of the histogram, we've got another image log. This is a threshold image log. And I've got it colored by the classes, the color map that we use to color the different classes. So class 1 is gray, class 2 is yellow, class 3 is orange, class 4 is red. So you can basically see the distribution of those different classes on a step-by-step, depth-by-depth, pad-by-pad basis as you scroll through your well. And if we come down to that conglomeratic section, you'll see we've got class 1 sitting right on top of it, and then we come into that conglomeratic section. This tells me there's been probably been a pretty significant seismological depositional change that's happened from the conglomeratic section to here. I can start making some inferences on that. But you'll see here I've got my different class logs displayed. I'm displaying these guys in a sort of cumulative fashion, so I can see which of these is the dominant class just from here. But the major class log here, on a depth-by-depth basis, it is telling me, which of those different classes is the majority class that I see across my image over that particular depth interval. Okay, and you'll see we start to see some reds, this class 4 in part of the conglomeratic section. We come down here and we start to see some laminated sections, and we're predominantly seeing class 2 and class 3. But yeah, so this, to me, visually, it's very stunning. But again, it's taking what we can we can infer or make some qualitative interpretations and actually putting some numbers around them and giving us a bit more of a quantitative interpretation. And like I said, it's visually stunning too, so I get pretty excited about that. We have another tool. So this one, you actually were responsible for picking the cutoffs for your different logs. Well, if you really want the data to speak for itself, which again is something that I tend to be a very big fan of, we do have a tool that will allow you to do that, and that is what we call dynamic threshold analysis. With dynamic threshold analysis, you're not going to input what your cutoffs are. What you are going to input is you're going to basically give threshold a value for, different cutoffs, right? So here I've got 3 different values, so I'm going to have 3 different cutoffs. You can actually use dynamic threshold analysis as a way to do image binarization. So if you were to set the first and third values to 0 and the second value to 2, that would be sort of a very dynamic way to do image binarization. And that's something some of my colleagues have done quite a bit. It's not something I've done all that much, but I do know it's something that's available to you here. So here, the biggest thing that you specify are your number of bends, and then how you're cutting, what you're using as a cutoff. In this instance, we're going to select median, but you'll see you can select mean or mode, and then what you're using as a modifier here. And again, the module help does a really good job of sort of going through and explaining what these different parameters are, and our online help does a fantastic job of explaining what you're doing with these guys. So in this instance, when we run this here, you'll see we're actually outputting a histogram log. Okay, this is going to be a little bit different to the histogram log that we generated here, just with the histogram analysis workflow, but mainly because we're using some different parameters to generate the histogram here. And you'll see we're going to output our different cutoffs, and we're going to output normalized cutoffs, and we're going to get another threshold image. This is a dynamic threshold image, and then we'll get those 3 classes in this instance. So if we take a look at the results from this. Okay, again, we use this equalized image to run the module. Here's our histogram. You can see that it's got a little more hotter colors than the original histogram did, but we still see the same kind of heterogeneity that we saw, and we still see the same kind of spread that we saw. You'll see here we've got our dynamic threshold image log here that shows us sort of a distribution of those different classes, and we can see the different classes and how they're distributed here. And you can play with different parameters within this module, depending on what you're trying to find or how you want to work. You can certainly play with this to see what the different outputs or different parameters provide as far as results go. Okay, so that does a pretty good job of covering our image analysis workflow. One of the things that I haven't touched on is generating high resolution porosity log, but for the sake of time, I'm going to leave that for now because I do really want to get into auto texture analysis. And we've got 2 methods for doing auto texture analysis. And we'll come back here, and I'm going to open up we're going to start off with self-organizing map, and then we're going to get into multi-resolution graph-based clustering. Now, I'm not going to go into the details of the differences between self-organizing map and MRGC, as I covered that as part of our electrofacies analysis rock type classification workflow that I did, I believe, back in June. And if you want to know more, I definitely encourage you to watch the recording of it, because I do go into a little bit of detail, actually quite a bit of detail, about the differences between self-organizing map and MRGC. Now, if I expand these 2 menu options here on our processing menu, you'll see that both of these workflows start off with the same steps: image normalization and parameter extraction. Now, this image normalization is not the same as the image normalization that you do when you process the initial raw image. Okay, so you have to run image normalization as part, you have to run this particular image normalization as part of the textural analysis workflow. But one of the really nice things is if you run image normalization under and parameter extraction under 2D self-organizing map or under MRGC, you don't have to run it again to do the other texture analysis. Okay, the results from these 2 modules are going to be exactly the same, regardless of whether you're working in the 2D SOM or whether you're working in the MRGC. Okay, So the first step, as I mentioned, is normalizing your image. Okay, so coming up with an image normalized image log. And we're going to get to see what this looks like in a bit. The next step in the workflow is parameter extraction, and that's going to output this feature log here. So, we're basically saying, take this normalized image log. We need to use the gaps too, because we don't want to, we've got spaces between our pads. We don't want to count that into the texture. We want to make sure that geolog ignores the texture. And we're going to output a feature log. Okay, and it's this feature log that we're going to use then to generate our texture map in this instance. And for self-organizing map, you're going to specify how many squares you're going to have along one side of your chart. Okay, in this instance, I left the default as 10. So what I output was a 10 by 10 grid, or basically 100 classes. You could specify 5 and you would get the 5 by 5, or if you wanted to do something simpler, you could do 3, so you would get 9 different classes, right? Or 9 different 3 by 3 image map, I guess. Now, if you're going to do texture analysis and you're going to do 2D self-organizing map texture analysis on a bunch of wells, you want to be able to adjust your map so that, the area that's, say, more homogeneous is in the same corner of all of your maps. What you'll find when you run this workflow over your wells is you're going to have an area that's going to show what I would say is more heterogeneous nature, and an area that's more homogeneous in nature. And if you're going to try and compare these maps across multiple wells, well, you're going to want to make sure you can orient them appropriately. And that's what this map texture adjust does. In this instance, we're just working with one well, so we don't really need to do that. But we take this map here, and we use it as input, and that feature log that we created as part of parameter extraction. And that's what's going to generate in this instance, you can think of it as our facies log. We're going to get a texture class number, and then we're going to actually get 2 other class numbers. One's by row and the other's by column. So we're going to get a class number for each of these rows, and we'll get a class number for each of these columns on a depth by depth basis. So when we run this, what we're going to see is something very similar to what we get here. So we've got the normalized image here, and here's the feature log. And my understanding is the more teeth that you see on the feature log, the more heterogeneity you see in your data. And you can see we've got our texture classes here, we've got our column class, our row class, and then this green log is just the number class log, and it's going to be going from 0 to 100. And then we get this really kind of bizarre visual 3D track on the far end. I'm not going to spend a lot of time on it, but it's one that people get a bit confused on. But really, it's meant to be a visual aid. So if you see this gray box here that you see on a maybe every few meters, well, that gray box, think of that as the boundary of this, what's essentially a cross plot between your rows and your columns. And these guys here, these multicolored flags, if you will, are basically pointing to a different area on the cross plot. So you can see I've got cursor tracking on, and the upper left of my cross plot or texture map, you can see I'm pointing to, that's where my cursor, this blue flag happens to be this guy here. Okay, so if I come up here to this teal flag here, you can see that's in the upper right portion. And if I come down here, these guys are pointing straight off to the left. They're more in the middle here. It's just meant to be a visual aid, really. Okay, we're going to do one last thing. We're going to leave the 2D self-organizing map, texture map behind. But first, before I do that, I want to say, one of the things that you can do to simplify this, if you don't want to just take these class logs here, is you can actually draw polygons on here. And you can draw polygons and output volumes. Basically calculate volumes based off of those polygons if you want to sort of simplify and say, okay, everything in this upper right corner is class 1. Everything in this lower right corner, or sorry, lower left corner or lower right corner, getting tongue-tied, is class 2, and so on. So you can basically draw your own polygons and come up with your own classes, or just sort of group these or lump these, if you will. And with that, I'm going to go ahead and bring up auto texture from multi-resolution graph-based clustering. And keep in mind the first 2 steps are exactly the same, okay? They're exactly the same as what we did for self-organizing map. Image normalization and then parameter extraction, okay? So we get that image normalized, we've got the feature log. What we're gonna then do is we're gonna create our texture map, okay? And this is where the big difference between self-organizing map and MRGC is. In self-organizing map, we specified we wanted a grid that was 10 by 10. Here we can say, I want you to try and find as many as, in this instance, 10 facies. So we're saying, I want you to find a maximum of 10 facies. And so what the tool is going to do is it's going to try and come up with 10 classes or 10 facies based off of the texture map. Okay, if it can't find 10, if it can only find 5, it will output only 5. And that is sort of the key as to how MRGC works. It's going to find the best number of facies up to the maximum that you specify. If it can't reach the maximum, it will give you the most that it can, as high as or as close as it can get. So we're going to use that feature to generate that map, and it's going to look something kind of like this here. It's fairly straightforward. In this instance, you'll see it found 9 different classes, okay? We set 10 and it couldn't find 10, but it gave us 9, which is fine. That's good. Once we've done that, we want to use that map MRGC in the feature log, and we're going to output our facies log or our texture class, what we're going to call EFAC. That is our texture class. So this is a little bit different, and in some ways it's a little bit easier to digest because we don't have to interpret the different class logs or the columns or that really weird visual 3D log. But as I said, you know, we get this normalized log, it's going to be the same. The feature log is going to be the same. The main difference is that we get one output, and it's just this facies log. So we can scroll through and compare it to our normalized image here, as well as our static or equalized images, and see if we can start making some inferences as to what's going on with this class log. You know, so maybe where we've got the teal is where we've got something that's, you know, a bit more resistive, where we've got the warmer colors might be where things are a little bit more conductive, as a for instance. And so with that, I'm going to sort of circle back here, and really what I hope I've done over the last little while is shown you. I just need to move this. Sorry about this, guys. What I hope I've done over the course of the last hour-ish is show you that there's a lot more that you can get out of your borehole image data, aside from, you know, structural information like what your dip direction is, what your bedding direction is, or even fracture analysis. There are a lot of things that you can do with image logs that I think allow you to take what can often be thought of as a qualitative tool and turn it into a much more quantitative tool for interpretation purposes. Okay. The other thing is if you're working within the geolog environment, you know, what we allow you to do, and this isn't something that I stressed earlier, and I should have, is that you can bring all of your processing in-house and work within geolog. We provide a vendor agnostic way to work with your data. So it doesn't matter if you're working with Schlumberger or Halliburton or Baker, or even Weatherford. We provide tools for taking all of that image log data, regardless of vendor, and QCing the images, speed correcting it, and processing it to output an image log that you can work within geolog. And once you've got that image log that you can work within geolog, you can then go through all of the image analysis tools that I went through, be it the thresholding analysis or fracture analysis or even structural analysis, which most people do is a given for most people. And if you can bring that in-house and you're working within geolog, then you can actually incorporate that information as part of your greater petrophysical interpretation. And you can start relating the texture that you see in your borehole images to what you're seeing from a porosity or permeability standpoint as you go through the rest of the rock characterization or petrophysical characterization of your wellbore. And with that, I think I'm going to wrap up.